Let us now look at the following question, which is one that is asked in your course pack. Consider pentane and butane 1-ol. Can differences in London dispersion forces be used to explain the differences in boiling points for these molecules? To answer this question, we need to go back to teaching model number 2 table and look at the data concerning these molecules. We are asked to compare pentane, which has a molar mass of 72 grams per mole, to butane 1-ol, which has a molar mass of 74 grams per mole. Although the molar masses are essentially identical, and as is the surface area, the boiling points are considerably different, 36 degrees Celsius for pentane and 118 for butane 1-ol. Clearly, butane 1-ol has stronger intermolecular forces. You may be wondering why I said the molar masses are essentially identical when there's a difference of 2 grams per mole. This brings us to an important point. Although the molar mass of a molecule is a reasonable indicator of the relative strength of London dispersion forces, a difference of 2 grams per mole is not sufficient to say confidently that we would expect the London dispersion forces to be different. If I want to make the argument for greater London dispersion forces, I would be looking for a difference of molar mass of at least 10 to 15 grams per mole. Therefore, I conclude that there must be something else at play that would explain the significant difference in boiling point and therefore significant difference in intermolecular forces. We need to look at the other 2 intermolecular forces, and these are dipole-dipole forces and ultimately hydrogen bonding, to explain these differences. Let us now take a look at the next information section related to dipole-dipole interactions. Here we have the electron density plots for the molecule acetone. I've drawn the structure for 2 acetone molecules so that we can highlight the intermolecular forces between these molecules. Now remember that the London dispersion forces are ubiquitous, so there are London dispersion forces holding these acetone molecules together. But the energy distribution plots also show that there's a degree of polarity in these molecules. Of course, we would have expected this based on considering the bond polarity and the molecular geometry, and we also saw earlier in the tutorial that dipole moment for acetone is considerably high. The red colored part of the diagram represents an electron-rich region, in other words, delta negative, and the blue colored part represents an electron-poor region, delta positive. Off to the side of the energy density plots, I'm going to insert bond line drawings for the structures of acetone. Now that we have some experience with labeling the polarity features of a molecule, I'm going to take a shortcut in labeling by inserting the partial charges and only the molecular dipole arrow. I will omit the bond dipole arrow. This makes the representation a bit cleaner. Therefore, in addition to London dispersion forces, there will also be dipole-dipole forces of attraction, that is, forces of attraction due to permanent dipoles in adjacent molecules. To simulate these interactions, I've included dashed lines. There would be the attraction between the delta positive region of one molecule and the delta negative region of a second molecule. Further, in general, the greater the molecular dipole, the greater will be the dipole-dipole forces. These extra forces of attraction add to the overall strength of the intermolecular forces. While London dispersion forces are ubiquitous, they are generally weaker on a force-by-force basis because they're due to temporary dipoles. Dipole-dipole forces, however, will only exist in polar molecules, and only through specific intermolecular alignments. The delta positives and the delta negatives have to be aligned, but they are stronger on a force-by-force basis because they're due to permanent dipoles. If we come back to the question, can differences in London dispersion forces be used to explain the differences in boiling points for the molecules of pentane and butane-1-ol, we know the answer to this question is no. Consider a representation of two molecules of pentane. The only forces that would be holding these molecules together would be London dispersion forces. Now consider a representation of two molecules of butane-1-ol. Notice that I represent the geometry about the alcohol group as bent, as would be predicted by Vesper theory. In addition to London dispersion forces that would be holding these molecules together, and in particular if you think about the hydrocarbon portion of this molecule, there will be dipole-dipole forces. Note that because the molar mass and surface area are similar for these two molecules, the London dispersion forces would also be similar. So the dipole-dipole forces in butane-1-ol are in addition to the already comparable London dispersion forces. We will see later in the tutorial that butane-1-ol also has hydrogen bonding forces of attraction, but for now we'll just focus on the dipole-dipole forces. Let us apply these ideas to some practice examples.